All right, I think we can get started so that we, in the benefit of time. It is thank you all for coming to the AstroAI lunch. Today it is my pleasure to introduce Fiona Redmen. Fiona is one of the Southampton students. I don't know if you know this, but every year we get about 5 excellent Southampton students to come to the CFA to do research here for a full year. And this year, Fiona is one of them. Fiona has been working with a few of us here at AstroAI on the problem of fitting the spectra, the X-ray spectra of X-ray binaries, in a way that makes it as interpretable as possible in terms of the actual parameters of the fit, using variational auto-encoders and normalizing flows. Fiona is currently a master's student finishing up in Southampton, and potentially will be around for a bit longer after the semester is over. So if you have questions for her or want to chat with her, feel free to reach to her directly. So with that, I guess the floor is yours, and I look forward to your talk.
Thanks. Okay, so my project is on spectral-fitting black hole X-ray binaries using machine learning. And so black hole X-ray binaries essentially consist of a black hole with a companion star orbiting and accreting matter onto it. The accretion mechanism can be modeled using 2 components, straight black hole, and we have this thin disk, which is optically thick, geometrically thin, and this hot corona of of electrons. So there's 3 main accretion mechanisms, emission mechanisms going on in the system. So there's thermal emission through the particles that are in orbit in the thin disk, releasing gravitational potential energy and releasing thermal emission. And these thermal photons also get Compton upscattered in the corona. And then finally, some of these Compton upscattered photons also get reprocessed in the thin disk. And we can then study the spectra produced by these types of emissions. Black hole X-ray binaries go through various states. So we have this hard state where this power law component from the Compton upscattered photons dominates. We have this thermal state where the thermal component dominates, and we have this SPL state, which is defined by the fact that the power law is much steeper. So it still dominates like in the hard state, but it's a lot steeper. And black hole X-ray binaries, there's like 2 major factors about them that we want to find out and that we can use spectrum to find out. So one of them is winds. We can look at the velocity of winds through the Doppler shift of absorption lines. As you can see in this graph, the Doppler shift is due to velocities. And then here we have a graph of various spectra of one black hole binary system going through outburst. So the spectral lines go from black to blue to green to blue to pink to orange as it goes through outburst. And you can see this absorption line, this ion line, gets deeper and shifts slightly. And this can tell us stuff about the ionization and the column density and velocity of the black hole. So, and yeah, so we can also look at the spin of the black hole through spectral fitting. So generally, Newtonian physics shows us that the spectral line produced in the accretion disk would be Doppler like split through the Doppler effect. But then when we add special relativity, this the bluer side of the line gets boosted. And then when we add general relativity, it gives this gravitational redshift effect. And we can add up across all radii the emission line, and we get this overall line profile. Now, the fact that the spin of the black hole affects this quite a bit, the look of this line as it changes the effect of the gravitational redshift. So as you can see, there's a much broader line produced by an almost Kerr black hole, which is rotating very fast. And this other line, which is much narrower and peakier, that one would be from like a Schwarzschild black hole. So you can really get the spin from the spectrum. And so my aim here is to be able to fit models to spectra to obtain the physical parameters of the black hole. And we're using nicer data, which is time-based and can capture dipole X-ray binaries across many states. And we have about 10,800 spectra. So we have a lot of data, which is why we are using machine learning. It can help us analyze this data much quicker than usual methods. So the model that we are using currently does not give us information on the spin of the winds, but this is like a step towards reaching that. So what we do is we model with photon absorption along our line of sight to the source. We have a constant upscattering component, which tells us the steepness of the power law and the amount of photons scattered in the constant in the crown. And then we also have this black body emission in the thermal component, essentially, which tells us the disk temperature and the overall brightness of the emission. So auto-encoders, essentially, they take input data and they reduce the dimensionality into this latent space, and this latent space then can be fed through the decoder to give us our output data. So in this case, our input data is a spectrum. We want to narrow it down to get our 5 physical parameters. So the parameters in the model that I just mentioned. And then we can also, use the decoder to reconstruct it. We compare the reconstruction with the input data through a loss function, and we try to make them resemble each other as much as possible to show that the parameters to ensure that the parameters in our latent space accurately represent the data. So we use this loss function, this reconstruction loss function with mean square error, and we also add this latent loss. And this allows us to get a latent space with actual physical parameters rather than arbitrary values. So the latent loss essentially measures discrepancies between predicted parameters and the parameters that the ground truth parameters. So yeah, and this was done by a previous student who managed to fit these spectra 2,700 times faster than traditional methods with comparable accuracy.
Thank you, Ken. So what is one of these parameters in the latent space here associated to the spin? I missed that.
Oh no, they're not.
Okay.
So the spin is what we want to do next. We want to develop this like state that we can with these more these more like easy parameters that we can fit for, and then we can use this to then find more subtle features later. So like kind of a working program.
And the input data, is it actually observed data?
Yeah, so yeah, this is real data. We can also train on synthetic, but I'm just using real for now. So yeah. So my work is essentially to obtain uncertainties in these parameters. So what I started off with was using just a general variational auto-encoder, which implements this latent space that is described by a Gaussian, which has a mean and a standard deviation. But and for this I used Gaussian negative log likelihood loss instead of mean square error loss for my reconstruction. So this takes into account the errors in the input data and weights the data points accordingly. And then I used a similar mean square error loss, and I also used this KL divergence, which ensures that this latent space has a Gaussian shape. But this didn't work very well because the parameters aren't very well represented by a Gaussian probability distribution. So I went on to using normalizing flows. So this still has the auto-encoder structure.
All right.
Yeah.
Could you go back for a second? So what is the second term here? The latent loss?
Yeah. So that compares the predicted parameters to the input parameters, and it ensures that the model learns physical parameters rather than arbitrary values in the latent space.
So you told me that the input was observed data.
Yeah.
So how do you know the ground truth values for those? Okay.
So basically, the ground truth values aren't necessarily ground truth. They're like what expect gives us when we fit the model to the data.
Okay.
So this is not necessarily this is emulating the expect model rather than actual physics. Okay. Yeah.
All right. Thank you.
No worries. So normalizing flows, what they do is essentially they find transforms between Gaussians and more complex distributions. So this allows us to get this more complex distribution. And so we feed our normalizing flow this context to produce these transforms, and this context is what we get from the encoder putting through the spectra. And so yeah, we have a slightly more complex structure here, but essentially we're getting out a more complex probability distribution. And then we sample from that distribution like in the other auto-encoders, and we feed that through our decoder to get our output data. And then we get a distribution that looks similar to this. And our loss function is pretty similar to the variational auto-encoder one, but instead of the KL divergence, we use this normalizing flow loss, which essentially just maximizes the likelihood of our ground truth values. And this is like the general, more detailed version of the model. So in our encoder, we have a bunch of convolutional layers and some linear layers. And then our normalizing flow is just made of 3 linear layers, and that produces our distribution. And we sample from our distribution in our latent space. And then our decoder is consistent of a bunch of linear layers and gated recurrent units. So yeah, this model was mostly found by the previous student, but I've just added the normalizing flow and yeah. So there's still like yeah.
So when you said you sample from, you just have to sample in the decoder space to get the posteriors out and eventually, like if you go back on one more slide.
Yeah.
So to get the actual posteriors in the top right there, you have to sample your latent space, right?
Yeah.
So do you have to do that intermittently, or does that just give you one shot, you get a posterior out?
Yeah, to get these distributions, I sampled 1,000 times.
Okay.
So it did take some time. But I'm sure that there might be some better ways to do it. I haven't done some time.
So, and, was there another question? Yeah, sorry, go ahead.
And on the same, yeah, exactly on the slide. I mean, the ground truth looks right now very Gaussian, right? So what makes it think be like the normalizing flow instead of
Yeah, so the ground truth is assumed to be Gaussian, but it's more the degeneracies between the different parameters that makes it not very well represented by Gaussian.
just to get more flexibility.
Yeah.
In the model.
Yeah. And it has been shown to perform a lot better than just assuming Gaussian errors, so.
There's an online question as well. Have you actually fitted 10,000 spectra with XSpec?
I believe so. I haven't done it, but my supervisor Jack has given me these values, so yeah.
So before you move on, so you're using the normalizing flow to approximate the function from which you sample the parameters. Is that what's happening here? So you input data, right? And you encode it. And then you are using, I understand the normalizing flow as a way to approximate a function, right? You start with some sort of Gaussian shape and then you transform it. So the function that you're trying to approximate here is the posterior itself, or is it the prior that you're initially using to sample, or?
It's the posterior.
The posterior, okay,
Yeah.
okay.
Does that answer your question?
I think so, yes.
Yeah.
I guess I still have to think about the architecture.
Yeah, it's a little
Yeah.
bit
Yeah.
more difficult to
Yeah.
wrap your head around. Yeah. Yeah. And then so my results, these results are quite preliminary still, but yeah, so these are our input parameters versus our output parameters, and each of these grid points corresponds to one sample from one spectrum. But this doesn't really show the distributions very well. So I've plotted them with, I've plotted 3 spectra with their distributions shown with multiple data points. So you can see kind of more clearly how they are distributed. You can see this green spectrum isn't very well represented here, but I think that's due to the fact that the expert prediction isn't entirely great as it's been pegged at this limit. So yeah. And then we can also plot these distributions a bit more clearly. So here, we have this blue distribution, which is quite well represented. And so are the others. The yellow one's a little bit slightly off. Yeah. And then here we have our Compton scattered parameters. So you can kind of see a slight symmetry between each of the parameters in this for each spectra. And this is because they are linked to each other because they're from the same model. So yeah, there's a slight correlation between them. And yeah, again, the yellow one isn't showing to be very well, that great, but yeah, blue one's my favorite. Yeah, and then again, we have this black body component, which shows a very, very strong symmetry, as you can see here. But yeah, and again, you can see that this yellow one, the error in the normalization is quite large. And this is why I think that the yellow one's not very good at representing the data. And then we can then take, we can have a look in at the correlations between our parameters and our latent space as well. And you can see the blue distribution, you can see a very strong cluster in most of the latent space, which kind of represents the small peak that we have. And the main thing that is interesting here is, again, is strong correlation between the disk temperature and the normalization. We also have a strong correlation here, but that's not seen in the other latent spaces, as I'll show you in a second. Yeah, so here, again, very strong correlation between the disk temperature and the normalization, and here as well. And again, you can see how much bigger the true errors are in this plot because the gray plots are a lot bigger. So, and then we can take our distributions and sample from them to create these reconstructions. So in the blue solid line here represents what our decoder produces, and the blue dashed line is what expect would produce with these sampling parameters. We can also then use the ground truth parameters to make our reconstructions, which look pretty similar to what our sample parameters look like. This looks great, but then when you sample many, there's this second mode that comes up. So I'm not entirely sure about what this is caused by, so I'm going to look into this soon. But yeah, it's kind of interesting to see. And then here again for the green distribution, it is a pretty decent reconstruction, but again has this extra mode. Yeah, and then the yellow distribution. So
So presumably that second mode, if you go back maybe to the previous slide, that second mode that you're seeing there in the posterior samples is associated to another peak in your posterior, I guess.
yeah, I would suspect that, but it seems suspicious because they wouldn't be predicting why would they come up as an extra mode in my distribution if it's not predicting the right?
Yeah, it doesn't seem to match the data, right?
Yeah,
So
I think it might be because my reconstruction loss was weighted quite low. So maybe if I increase that, it might even out. But yeah.
And the other question is these ground truth curves here in gray, because they come from fits to the data using expect. Is that where this ground truth comes from?
The ground truth is essentially it uses the ground truth parameters that expect gave us.
So I don't remember what, so the distribution here, the gray distribution comes from sort of the uncertainty that expect gets for that parameter using some sort of chi-square or something, or not chi-square, but what is it? Whatever, hash statistic or something that expect uses.
Yeah,
Okay.
it's what expect uses, and it's the error in the expect.
Okay.
And then we can also look at the overall parameter distribution. So this is not corresponding to one single spectrum now, this is corresponding to many. Again, we see this very strong correlation here with our temperature and our normalization. We don't see it so much here with the normalization and NH and this temperature and NH as we did in our blue plot. So, yeah. But you can also see that the distributions of each parameter overall match our input distributions. So that's a good sign. Yeah, and then finally, we have this, the reduced PG stat, which essentially measures how good the reconstruction is. So our pre-calculated values give us a reduced PG stat of 4.4. So this is kind of a good reference point. The time isn't so relevant here because this is a really rigorous method of calculating the parameters, so it's going to take a while. But then this expect-fitting takes about 300 seconds for 60 iterations and gives us a similar reduced PG stat. So this is a good point to reference point. The previous model used essentially it used much less time, so on the order of about 3 nanoseconds, much quicker, but it gave us a reduced PG stat of 62, which is very high. But then what the student did was he used an extra 10 fitting iterations of expect, and this got the reduced PG stat much lower to comparable values, about 4.76. So yeah, but I'm not using these extra 10 iterations, and I'm still getting a reduced PG stat of 6, which is pretty good with a similar amount of time as well. So yeah. And then so in the future, I'm going to be using transformers instead. I'm looking into using transformers instead of convolutional and data recurrent unit layers, because these might establish correlations between spectra, parts of spectra and parameters a lot better than just the convolutional and the data recurrent unit. And then also I'm looking at replacing the Gaussian negative log likelihood loss with Poisson Gaussian statistic, because this represents the error in our data better, as it's Poisson counts and Gaussian background. And then also, again, finally, more further down the line, we can start to fit for the actual parameters that we care more about, like the spin and the winds of the system. And so, in summary, black hole X-ray binaries can give us spectral black hole X-ray binaries can give us information on the winds and the spin, and auto-encoders can fit these spectra way faster than traditional methods with comparable accuracy. And variational auto-encoders allows us to gain posterior distributions and much lower PG statistics.
All right, thank you. Marcus?
Great talk. Can you go back to the way you describe your variation auto-encoder model? And just I was thinking though, these results have been fitted on one particular data set, right? So this is nicer data.
Yeah.
So if you would go to another data set with different noise properties, you would need to retrain that, or
yeah.
So my question is, I mean, I'm not an expert in expect by any means, but it's probably a pain to run, I suspect, and it's quite computationally expensive. So one of the generalizations of this could be to emulate expect, and potentially, right? So not the just the expect prediction, you know, and potentially one thing that one could do is extend this from variation auto-encoders to conditional variation auto-encoders. This isn't a big step, potentially. So where conditioning variables are these quantities of interest that you really care about. I'm not sure what you really care about, that's totally problem dependent, but you can probably find a set of parameters, subset of parameters that you would like to include there in your conditioning, and then you could use conditional variation auto-encoders to try to emulate expect. Is that something that you thought about? This is sensible.
So what do you mean by conditional? Like,
so for example, spin. So you train a variation auto-encoder, but you're not obtaining a distribution, a normal distribution, but a conditional distribution. So conditioned on parameters like spin or quantities of interest, and that allows you to do a lot of things. For example, you could use that as a substitute for likelihood functions, for example, right? So because likelihood data given a bunch of parameters, and these parameters could be in the conditioning here. And it's not super difficult to extend variation auto-encoders to traditional variation auto-encoders, it's 5 lines of code typically.
Okay,
Might be a low hanging fruit.
that's very interesting.
Maybe something you could discuss afterwards,
Alright.
if you have good suggestions. Phil, did you have a?
Yeah, so, I'm worried about this tail in your posterior, this like low mode that's popping up and
Yeah.
and what I worry about is I worry that you're training on noisy data that may not have all of the noise characteristics known, right?
Yeah.
So have you trained this and run this on mock expect data where you know the noise, you know the truth?
Yeah, no, so I haven't done that yet, but it's definitely something I've thought about doing. But I figured I'd like when I'm done with like training my model, perhaps like adjusting the hyperparameters and such, then I can look at training it on a lot of synthetic data and then afterwards training it on the real data. So it captures the actual physics, but then also has this sort of effect.
Yes, the advantage of training on mock data is that your ground truth could be just the actual ground truth that you input in. I mean, maybe I misunderstood, but this ground truth that you're comparing to is always kind of what expect gives you as the fit to the data.
Yeah, so
And I
it's-
guess we can assume that expect will do a good job, but does it really?
Yeah, it's
And is it
really-
actually capturing the actual parameters? That's something that, relates to what Phil was just saying, but.
Yeah.
Okay, any other comments, questions? Adam?
Just a quick question about normalizing flows. You've got the F1, F2, Fn.
Yeah, so these are the transforms which describe the transform between a multivariate Gaussian into this more complex multivariate distribution. So this allows us to be able to, if we know the transforms to get to the more complex distribution, we know how to transform back, so we can.
In order to use this component of the loss, the latent loss, so that there you're just comparing these values
Yeah,
to the ground truth values, which were the fits from expect.
Yeah.
That means that your encoder is the objective of the encoder here with the normalizing flow is to actually regress on these quantities. Is that correct? So you don't get just a random latent space, but actually, physically because you've trained it to point to these values. Is that okay?
yeah. There's another method that we also use on top of this, is that we train the decoder by itself at first. So we train it with physical parameters and we compare it to real data so that the decoder knows how to take physical parameters and produce spectra from that. And then we train the whole thing together with the decoder frozen. So then the encoder is forced to produce these parameters that the decoder can take as physical parameters.
Yep.
One last question. So when you fit expect, how many parameters are you using there? So how big is the latent space for the
yes.
expect?
So there's I think there's 5 parameters.
It's also the same 5 parameters that you have here.
Yeah. There's 2 more parameters, but they're fixed. So
Did you check that in the expect fits there are no problems with lack of identifiability or modeling specification error? Preferably double peaks.
I didn't do the expert fitting. I was just doing the data, so I'm not sure. But yeah.
Yeah, because you saw this double peak. It
Yeah.
might also be expect problem, I'm not sure.
Mhm.
But it's not around people derived from expect.
So it's bad on.
No, but the double.
Ah.
Maybe one final comment I had was you spoke about that correlation between normalization and
Yeah.
temperature.
Oh yeah.
Do you have an interpretation for that? Is that an actual correlation? Is it like a degeneracy in the model or
Yeah.
what is
So
it?
I think it's a degeneracy because the distance from the normalization, increasing both of them increases the amplitude of the spectrum. So they have the same effect on the spectrum. So if you were to increase the normalization, you can then decrease the temperature of the disk to gain a similar to obtain the same spectrum as you would if it was switched. So that's why they're like inversely related. So like increasing the disk temperature kind of decreases the normalization.
All right. If there are no more questions,
Sorry,
yes,
Jack, you wanna unmute yourself and ask your question?
Sure. Yeah, sorry, I was just responding to, I think, what Marcus had asked and wanted to relay that in terms of model misspecification, there's no significant such concerns with the model. You know, this is sort of a simplistic approximation to more complex, more rigorous models. But broadly, it does quite well over the range of observations that we explored here.
it's not in approval of your explanation, so you can have the conversation later.
Okay.
All right, well, yes.
Just one comment, you have been using auto-encoders, and I know it can take time to, train them. I mean, are there not other, techniques that you can use for dimensionality reduction and stuff, like maybe principal component analysis along those lines, which may take even lesser of a data and give you even faster results? Just as a thought.
Yeah, that's a good point. I haven't really thought about it. I've only really been looking into auto-encoders.
But principal component analysis kind of like does the same thing. It reduces the dimensionality and try to see which components are more relevant to your output.
Okay, that's interesting.
I mean, an autoencoder is like a nonlinear PCA, right? To some extent, so. Is that it? You guys happy with only half an hour so you can go back to your days? Thank you so much. In another week.